So just a quick little review thing. After yesterday's recitation, Caleb said he just spent a lot of time explaining this. Do you understand how this and this mean different things? Okay, so like if I said a sub n was 1 over n, and then the sum of 1 over n, what happens to the limit as n goes to infinity of just a sub n? That goes to 0. Okay, how about the sum from n equals 1 to infinity? As in like 1 plus a half plus a third plus etc. forever and ever and ever. That thing goes to infinity. Okay. No, well, I mean, you could pretty quickly add together a bunch of terms and have it get over 2, right?
Yeah.
So if the kicker is the list, the things that you're adding go to 0, but when you add them all up, it's not 0 anymore. Does that difference make sense?
Yeah.
So, and also, you have to be picky, because if you do not write this sum sign, you mean a sequence. You see what I'm saying? And without that sum symbol, it just means the list. Put in the sum symbol, it means add up stuff in that list. So they're related. So tell me one thing, and then we'll move on to this integral test. So if the limit as n goes to infinity of the sequence is 0, then your series a sub n converges. True, false?
False.
That is so false. Ain't nobody better say that's true, okay? That is so false. It's true if you do it in the other direction. If the series converges, then the limit is 0. How about this? If the limit as n goes to infinity of a sub n is not equal to 0, then what do you know about the sum? Then the sum diverges. Because what that means is the stuff that you're eventually adding up is getting close to some constant. You're adding like a half plus a half plus a half an infinite number of times, and a half times infinity is still infinity. Okay, so what is this thing formally called? Test for divergence. There is no singular test for convergence. Okay, there's a bunch of them. But I have students every year, especially in my distance class, make up stuff like, oh, by the test for convergence, because the limit is 0, the series converges. It doesn't work that way. It's not that simple, and I'm not withholding information from you. It isn't that easy. If the limit is 0, the series might converge, it might diverge. You just don't know. You got to do something else. If it's not 0, you know it diverges. So always check for this first, but don't erroneously conclude that the first thing happening means convergence. Once that limit is 0, might converge, might diverge, got to do something else, okay? And one of the something else's that you can do to prove convergence is this thing called the integral test. So somebody already observed that this is kind of like the integrals, like when we do integrals that have infinite bounds, and that somebody knows who they are. Well, I keep picking on that somebody. And so this integral test relates these things, these series, to integrals. And there are some conditions that must be true about the function that you're integrating for this to work, but in general, it's pretty easy to see why this has to happen, okay? So first of all, 1 over n squared is a lot like the function f of x equals 1 over x squared, right? Okay, so let's draw what 1 over x squared looks like is a decreasing, and we only care about the positive part of it because our series goes from 1 to infinity, so we don't care about negative bits. So it looks something like, that isn't drawn to scale, but whatever. So f of x equals 1 over x squared. Okay. All right, now I am going to draw a sum, an approximation using right endpoints on these intervals, and why I'm going to use right endpoints is true. Well, you'll understand in a second. So, for example, I'm going to go up to 1 and draw a box under the curve. 2, draw a box under the curve. 3, box under the curve. 4, box under curve. Those boxes are not drawn to scale at all, so don't interpret my scale as meaning anything in here. What is is everyone okay with that picture and where the boxes are? Okay, what's the height of the first box? 1, because you get by plugging 1 into your function, right? So this is 1 over 1 squared, which is definitely 1, right? What's the height of the next box? 1 over 2 squared, or a quarter, right? Because and also that's the area of the box, isn't it? I should have been asking that question. What's the area of the box? But because the base is 1, the area is just the height, right? Because base times height gives you 1 times height gives you height. What's the area of the next box? 1 over 3 squared, 1 over 4 squared, etc., right? Okay. So then, do you believe that the sum from n equals 1 to infinity of 1 over n squared, well, that's equal to 1 over 1 squared, plus 1 over 2 squared, plus 1 over 3 squared, etc. That's what this is, right? I.e., this is my boxes, right? As in, the sum is represented by those boxes. So far, so good? Okay. Now, the one thing that's a little bit fussy with this particular example is that that first box is under part of the curve that has an infinite discontinuity, which makes it a little bit tricky to compare it to the integral. But do you believe this? That if I have this sum from n equals 1 to infinity of 1 over n squared, that is less than or equal to, I'm going to put a blank here, plus the integral from 1 to infinity of 1 over x squared. Okay, so first of all, we're going to fill in that blank with a specific number. So first of all, why can't I do the integral from 0 to infinity? What's the problem with that? That infinite discontinuity is a problem, right? So I have to start at 1. Now, the other thing is, so what is the integral from 1 to infinity of 1 over x? What is the area under the curve from 1 to infinity? So that's like all this stuff, right? You see that? So this integral is certainly bigger than the sum from 2 to infinity, right? And what could I add here to ensure that it's true for even 1? I could just add a number 1. Does that make sense? Because that 1 would just add on the area of the first box. You see what I'm saying? So this 1 there, that's the first box. Does that make sense? So we have that, but you agree that at least from this box, this box, this box, the sum from 2 to infinity is less than the integral from 1 to infinity, right? You buy that? Yep, and so to make it true for n equals 1, we had to add on that first box. Okay, that's really the only fussy thing about this argument. Now, if you work this out, like if you work out that integral, that actually is equal to 1. Like you can do a limit and work it out, but you guys get the details. So this right-hand side is equal to 2. Okay. So what do you think you can conclude? What can you conclude about the sum? It converges. Now, there's a couple technical reasons why, but at least from the picture, you believe that this is going to happen, right? Give me a nod or a... Yeah, okay. So just a couple technical reasons that I have to mention. Okay, remember that a sum or a series converges if the sequence of partial sums S sub n converges. And S sub n is just like the number of things you've added. You add the first 10 things, first 1,000 things, first million things. Okay, and the technical reason that you know S sub n converges, it's by something called the monotonic sequence theorem. And for that, you need two things. You need your sequence to be monotonic, which means either it's going up or staying the same, as in it's non-increasing or non-decreasing. Like it's decreasing or leveling, or it's either decreasing and leveling off or increasing and leveling off. So do you believe that this S sub n's, when you add things on, is going to be increasing? Like S sub 1 is just 1 over 1 squared. S sub 2 is 1 over 1 squared plus 1 over 2 squared. S sub 3 is 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, right? So you believe that S sub n is increasing? Yeah, so S sub n is increasing as you add something positive to get the next term.
Is that 1 over 1 squared plus 1 over 2 squared?
Yep, because what S sub 2 means is add the first two things in your series. The first thing is 1 over 1 squared, the second thing is 1 over 2 squared.
Yeah.
Does that make sense? Yeah, my bad handwriting. The other thing that has to be true is so we know these S sub n's are increasing, we also have to know that they're bounded. As in there's a number of fence on top that keeps them stuck. So what fence keeps them stuck? What number? Even better.
1,
2,
2.
right? We know that the sum is less than this number 2. So 2 is the number that fences them in. Bounded above by 2. And so just one thing to point out here is that this fact that S sub n was increasing is because you had a positive function, right? That means you added on something positive. And if that's not true, you cannot use this test. Okay, so this came from the fact that your function f of x is positive. And if f of x wasn't positive, you wouldn't have increasing anymore, and this test won't work, at least not all the time. Okay, and the integral is the part that gives it bounded above by 2. But the main point is that the series and the related integral do the same thing. Like if you can prove that the integral converges, then the series that has that inside of it also converges. Okay, how about this one? What's your suspicion? Like if I had given you the integral from 1 to infinity of 1 over root x dx, do you remember what that does? It's a converge, diverge, it's one of those P things.
Diverges.
This diverges. Okay, so the picture of 1 over root n looks awfully similar, right? It doesn't decrease as quickly as 1 over x squared does. Okay. So in the previous example, I wanted to show that that series converged, which meant I wanted to put it under something, so I got it fenced down, right? If this one's going to, bunch of this diverges, how do you think you're going to go about that? Something below it diverges, so this has to be bigger than the other things. So instead of using left endpoints, which give you an underestimate for this kind of function, I'm going to use, I used right endpoints last time, right? This time I'm going to use left endpoints. So there's my, and now I have, this is also going to give me a sum, and the sum is bigger than the integral. And this one's actually easier because there's no fussing about that first term.
Well, it still can't be 0.
But this one, the first term isn't 0. Yeah, so what is the area of that first box? Like this is allegedly a graph of f of x equals 1 over root x. So 1 over root 1, right? The second box is 1 over root 2, right? Third box is 1 over root 3, etc., right? So do you buy that this sum from n equals 1 to infinity of 1 over root n, without any fussing, is, sorry, excuse me, dyslexia. How is that related to the integral from 1 to infinity of 1 over root x? Which way should the inequality go? Greater than, yep. You could even be, say, or equal to, because it doesn't really matter. But the things in this sum, you're adding up 1 over root 1, plus 1 over root 2, plus 1 over root 3, right? That's the area of all those boxes added up. And they're above the area under the curve, which is just that part, right? Okay. So since this guy is infinity, as in it diverges, it forces the sum to do what? The series to be bigger than or equal to infinity, i.e. the series 1 over root n is going to diverge. And the reason you place the boxes the way you do has to do with what you're trying to show. If you're trying to show convergence, you have to have your boxes less than something that converges. Divergence, they must be bigger than something diverges, which forces it down or forces it up. We're going to use a similar idea in Friday's lesson, which is about something called the comparison test, where you do something but not with an integral to the general series.
Right, can you say that one more time?
Yes. So if you're trying to show convergence, you want to put your series under something that converges, which is what we did in A, right, the first one? Does that make sense?
Yeah.
If you want to show divergence, you put the series, how would that change? Over something that diverges. You're not going to have to, use pictures like this to prove stuff on your homework. This is just an idea so you believe why this test works. And it comes from this basic idea of comparison, which we'll formalize even more in section 11.4. But this is the reason why we place the boxes the way we did in examples 1 and 2. Awesome. Okay, so here's what this test says. So, in order for you to use this test, you have to check that the conditions are met. So the first thing is that your function f has to do 3 things. It has to be continuous, positive, and decreasing. And I think
Increasing, it just diverges.
Say that again?
If it's increasing, it just diverges.
If it's increasing, you would have to apply a different test. I'm not sure if it would diverge or not. It depends on how quickly it increases and then what to. I'm not sure if an increasing function would always imply divergence. I'm not sure. Okay?
Inverse tangent.
Inverse tangent definitely does diverge if you do a sum, right? Because that's the test for divergence. If you do a sequence, it doesn't diverge, right? Okay, and so suppose you have a continuous, positive, and decreasing function on the interval from 1 to infinity, and your a sub n equals f of n. So the other thing that's kind of flexible is it doesn't have to be 1 to infinity. It really could be some number a to infinity, where a is any number. That's at least for certain parts of it. The decreasing part for sure. The continuous, you just have to be continuous everywhere that you care about. And you know that the series is convergent if and only if the improper integral is convergent. And what this implies is that if your integral converges, then the series converges. And if your integral diverges, then your series diverges. The if and only if is a mathematical thing that lets you go both ways in the implication. If first thing happens, then second thing does, or vice versa. That's what this whole if and only if means. It means the condition can reverse. And the basic idea is that the improper integral and series, i.e. the sum, do the same thing. And for certain functions, you know how to find improper integrals, right? As in, you can do that. Now, one question that I want to talk a little bit about why those conditions are necessary. Question, what was it going to be? Oh, it was there and then. Oh, I had a question that was really important and useful and I immediately forgot it because I'm old. Okay, yes, I got it back. Okay. This is a conclusion that students make. Does the integral test tell you what your series converges to? No. And the answer is no. It tells you that it converges, but not what to. For the integral, you're going to get a specific number that it converges to because you can work out the integral. And the sum of the series is related to that number, but you just know that it's finite now all of a sudden. Okay. So let's talk a little bit about what's needed, or why those positive and decreasing is important. I think continuous is pretty obvious because if you don't have a continuous function, you have like infinite discontinuities possibly. Yeah.
And how come in the first example that it was bounded by 2? If it's not, if the interval is
The integral only has to be continuous on the interval from 1 to infinity. And that function in an example, you're looking at 1 or 2?
first example.
In first example, that 1 over x squared is continuous from 1 to infinity.
But if the interval test doesn't tell you what it converges to, why come the sum is bounded by 2?
The sum in that one is bounded by 2 because of the value of the improper integral. But bounded by doesn't mean it converges to. It just means that it converges to a number that's less than 2. So
you don't always have to add the first term?
in that one, like if you were looking at, if you were trying to make a comparison, like if you're trying to compare the value of this to the value of that for a convergent thing, you'd always have to add the first term to get like an upper bound, like we did in that previous example. So you could always say that the sum of a sub n's, if you have a convergent thing, is less than or equal to a1 plus the integral from 1 to infinity of that function. You could always, but you're not going to have to do stuff like that.
Okay.
But that would be the exact same picture for every single one, for every series that every convergent thing. And for the divergent thing, it's not really, they're both going to be infinity. Yeah.
So if you had, as you said, it could be from A to infinity,
Mhm.
some as n equals 4 to infinity, would you have to change the interval?
Yep, if your sum went from n equals 4 to infinity, your integral would change to 4 to infinity instead. And there are some series where we have examples, like today and tomorrow, where your series begins at 2 because it's undefined at 1. And so you just start your interval from 2 to infinity or 5 to infinity. It doesn't really matter. And so, yeah. Yes?
Can you work around a point discontinuity?
Probably if it's the right kind, but we're not going to do that. Does that make sense? It's
makes
probably
sense.
possible, but we're not going to do it.
Okay.
So it's probably possible to round discontinuities that are singular points as opposed to infinite ones. Yes, but we don't go that crazy in this class. Okay, so condition 1 was that your function f had to be positive. And just fill this in, there's some blank space there that you can use. Positive. That ensures that your Sn, your sequence of partial sums, is increasing. We discussed that with the first example, right? As in you add some positive thing to get the next term in your sequence of partial sums.
Are there going to be problems that try to trick us by not meeting these things?
Not necessarily, other than there'll be a couple questions that might say, like, why doesn't the integral test apply to this function? Does that make sense? And then you'll be able to say, okay, because it's not positive, that's why it doesn't apply, or because it's not decreasing. And I think that one's pretty obvious. Now, the reason that f needs to be decreasing, this is because of our boxes. And what I mean by that if you have a decreasing function, what does that ensure about your right sum? So f decreasing means the right-hand sum is an underestimate. It's always less than, right? Less than integral. And then what about the other side? What about if f is decreasing, what does it tell you about the left-hand sum? So the left-hand sum would be the ones that looks like this, right? So how does that left-hand sum relate to the integral? Greater than the integral. And so that's what allowed us to make the conclusion that, okay, we have this value that's less than a finite number or bigger than a finite number. That's what these things are used for. Yeah.
So would this work if it was a negative increasing function?
You can make negativity kind of work, but we're not going to go there, so let's just not talk about it. So for now, because there are ways to futz the test to make it work for negative functions and stuff like that, but we're not going to bother with it. Okay, a couple notes about this, then we'll start your quiz today. So we've already discussed you don't have to start at n equals 1. So for example, we're going to have the sum from n equals 2 to infinity, 1 over n ln of n. And you can't start at n equals 1 for that because you have an undefined thing, right? So if your series begins at 2 or 5 or 7, just start your integral at the same value. Okay, so like that one's an example where your series won't sum 1 over n ln n has to begin at 2. The other thing that there's a little bit of flexibility is you don't always have to have that f is always decreasing. It just has to be the fact that it's ultimately decreasing, like eventually. So for example, like a little picture of that, your function could oscillate, but then eventually decide to decrease in a nice smooth manner. And the point is with those first few terms, you could just approximate them with like the maximum on little intervals. But with this one, you have to eventually get to a point where your thing decreases. And if this happens, you just have to tell me, or your grader, when your a sub n's, or your function actually really, when your function starts to decrease. And we'll do examples of that.
What kind of function would do this that isn't a piecewise function?
Well, there could just be a function that does some kind of like jump and then goes down, right? I mean, that happens. So it's not uncommon. It's just telling me that from 5 on, this function is decreasing. Okay, I want to talk a little bit about when you can say something is obviously decreasing and when you can't say obviously, because I just want a really cut and dry reason so I can tell you, no, you may not say that. So you can say things are obviously decreasing with a little bit of explanation if the numerator is a fixed constant, and the denominator is a simple increasing function? For example, 2 over 3x plus 1. I think it's pretty obvious when the denominator gets bigger, the result gets smaller, right? Okay. When can you not say obviously, and all other cases, okay, as in like constant over function, sure. Function over function, no. For example, stuff like f of x is x over x squared plus 1. I don't know. F of x equals x. Yeah, not really, actually. I mean, like, x and x squared plus 1 are both increasing, and the question is relative to each other, how fast do they do it? So it's not obvious. How do you prove increasing, decreasing? You have to use a derivative. So use f prime of x in these cases. And we'll have examples, but that's how you can tell if you have to use a derivative or if you don't. Okay? Yes?
So in the previous example, if you just use the derivative rather than go into the it's obvious.
And that also works. It's just that on some of those examples, the derivative might be kind of hard to find.
We also just like divide by x over x. No? You have a constant over.
I think on that one, on the first one you could. You should already do that, I think. It's not having somebody do that.
Okay.
Something like what?
Something like e to the negative x.
E to the negative x would fall under the category of just stuff in the denominator, because 1 over e to the x.
We need a few more.
There were some in the back, I've already gave them some. I lost count. 1, 2, 3, 4, 5, 6. This room might have issues. They're coming, I'm sorry. You can stay 5 minutes over because I was slow if you want to. So when you're applying the integral test to show that a series converges or diverges, it's not going to tell you what the series converges or diverges to. And if you think about it correctly, it might give you like a bound, but you're not asked to do that. You're just asked to determine, does it converge, does it diverge? Because once you know something converges or diverges, you could just estimate it by adding up like a certain number of the terms, right? And then add the first 100 terms, ask a computer to do it. That wouldn't be so hard, right? But so the one thing you have to know is that when the directions say to apply the integral test, that always implies that you have to check that the test applies.
So check for the positive, decreasing, continuous.
Check for the positive, decreasing, continuous. There are 3 things to check every time for this, and 2 of them are pretty easy. Like continuous is not very hard, right? Positive usually isn't very hard either, and decreasing may or may not involve a derivative. It just depends on the situation, okay? So for this one, let's just start with the easiest one. Let's start with continuous.
You need the I for n in order to be discontinuous.
Yeah. Exactly, yeah, this denominator will never be 1. So the other thing is you're going to integrate, so you need a function. So let's start by making a function, f of x, and that function is just 2 over x squared plus 1. And tell me, where is this thing continuous?
Everywhere.
If I say, have you guys seen the symbol for the real numbers before?
Yes.
Yeah. Oh, man. I thought I had my eraser selected and I had my other whatever. Okay, so it's continuous. Nope, that won't erase, I guess. On R, which you could also say negative infinity to infinity. It's not necessary that the function be continuous like that much, but just state that you know that it's continuous everywhere if it is. Okay. Is f of x positive? F of x is bigger than 0 for all x. Or for, you could have also said on R. And I think that's pretty obvious because you're squaring stuff and doing 2 divided by some positive number, right? Okay. So, we got positive. Okay, then we'll check decreasing. So this function isn't going to be always decreasing. Actually, I'm pretty sure if you draw a graph of that function, it looks something like this-ish. It has symmetry, actually, but it looks approximately like that. So when does it actually decrease? From 0 to infinity? Yep, and so how you state that sort of formally is you say that for x bigger than 0, what is the denominator doing? So what is this, as you plug in bigger and bigger x's, what happens to x squared plus 1? It increases, right? For positive x's, x squared plus 1 is increasing. And then what happens when you do like a constant over something that was increasing? Now, therefore, this thing.
It's almost synonymous with therefore.
Yeah.
So you don't have to do the derivative.
Nope. Although it wouldn't be wrong to do so. Does that make sense?
derivative-
Like for this one, the derivative would almost be faster on this one, but we will have some instances where the derivative won't be faster. But with this one, the derivative wouldn't be hard. I think it would be negative 2n over n squared plus 1 squared. And that would be negative as long as x was positive. So you're totally welcome to use the derivative, but just give me some argument. Okay, does that make sense? Okay. And so now you apply the integral test, by which we mean like actually do the integral. So you find the integral from 1 to infinity of 2 over x squared plus 1 dx. And if this thing converges, then your series will converge, and if this integral diverges, then your series diverges. They just do the same thing. So I'm sorry, you use the correct notation. You say limit b goes to infinity, integral 1 to b. I'm so sorry. My stats professor doesn't make me do that, and I'm afraid I cringe every time I plug infinity into a function. But so take stat 651 and you can plug infinity into functions, but not this class. It's a pretty easy function to anti-differentiate, though, isn't it? Yeah. What's the antiderivative of 2 over x squared plus 1? 2 arctan of 1? Arctan x?
Wait, what happened to the 1?
Well,
Oh,
the
because
two,
arctan.
that's just arctan's derivative, right? You just have to know that. Is that all right?
Yeah.
No, I was forgetting something.
What WebAssign is going to do to you, just FYI, to make this problem be randomized, they're going to make that number into things like 4, 16, 9, 25. Remember
But then
that?
you can just do the,
1 over a arctan x over a formula. Remember that?
They were gonna turn it into a number that doesn't have an easy square root.
Well, then you would just do arctan x over root of 5, for example. But they typically tend to keep things, if they randomize stuff, and it has that property, like where it has a perfect square root, they tend to keep this consistent, from what I can tell at least. Like they would either make them all have perfect square roots, or they'd make them all not have perfect square roots. It'd be one of those two, I believe. I could be wrong.
the arctan of infinity is actually not that bad.
Yeah, and the other thing is that arctan of infinity isn't 0, right?
Yeah.
So 2 arctan b minus 2 arctan 1. Sorry, I just changed notations there. Didn't mean to do that. Yes.
Would we not be adding by like 2 or something, like the first term in the sequence?
I think what you're trying to do is to provide an overestimate of what the sequence of sum is, and you don't have to do that. Because we did that in the proof to sort of prove that the integral and the series did the same thing. But this test, what the test tells you is that if the integral converges, the series converges as well. It doesn't tell you what to, it doesn't give you an upper bound, it just says that it converges.
Okay.
But what you're trying to do is to add in that first term so that you could say that, oh, well, my series is less than or equal to this thing.
Okay,
That's
so you don't need the first term?
You don't need the first term. If you wanted to say the series was, and do some comparison to this to get like an estimate for how much it could be at the worst, then you could do that, but you're not gonna ever have to do that in applications of this test.
Okay.
Like step one is just to figure out if the series converges, and then step two, later on we'd figure out, like, okay, once I know it converges, how could I estimate it? And we'll have an even better way than the one that you're describing.
All right.
That looks like pi over 4.
Yeah, so where does arctan go as this thing inside it goes to infinity?
Oh, wait, I forgot the
Pi halves, great, so we've got 2 times pi halves.
So you get
pi minus,
And then how about tan inverse of 1? I can't give you an easier function number to put into tan inverse. Pi over 4, yep. Minus 2 times pi over 4.
sorry, pi over 2.
So it's okay, you see me make a gazillion mistakes. Pi minus pi halves, which is pi over 2. Yeah, so there are some values of like arctan for which you're not going to be able to evaluate them easily, but, so that tells you the integral converges to pi over 2. So you don't know the series converges to that, but now you know that it converges. So you can, just like write a conclusion. So since the integral from 1 to infinity of 2 over x squared plus 1 dx converges, and I think it probably is just best to write down your series so it's clear what you're talking about. The sum from n equals 1 to infinity, be specific. As I've run into problems with students when I wasn't specific, and I think it probably is just best to be a little bit more specific with these things. So, there's kind of like 3 steps there, right? Check the conditions, find the integral, make a conclusion. Yes?
Isn't a series really like an integral where the subintegral is 1?
No, because an integral is an area under a curve, like a smooth curve, whereas the series is,
I mean, like a Riemann.
a Riemann sum is an approximation. That's okay. A Riemann sum is an approximation of like an integral, an area under a curve, but in order to have it be the area exactly, you're doing a little bit of a different thing. Like what happens with, in those instances, this one, the delta x is always 1.
Yeah.
In the Riemann sum, your delta x is getting smaller and smaller and smaller and smaller and smaller. It's not constant. Because as you increase the number of pieces that you make, that makes the delta x littler, which makes many more boxes, and then like at the end an infinite number of boxes than this one makes. So no, they're not the same thing. A Riemann sum estimates, and like if you take a limit of Riemann sums, then yes, you do get the integral as the number of pieces goes to infinity. But this thing, the delta x is always fixed at 1 and doesn't change. You never take more pieces. So they both have that infinite upper bound, but what the n stands for is different. In the Riemann sum, the n is the number of pieces, and in this case, n isn't like the number of pieces anymore. So I think that's they're not the same thing. They just both happen to have sigma notation. So.
Next problem is that your word is.
Well, how so?
Well, kind of. It's got that +4 thing.
Except for, okay, so
Factored.
okay, so we have check for continuous. So your function is f of x equals x over x squared plus 4. Is this continuous? Yeah, that's continuous on R, negative infinity to infinity. Okay, check positive. F of x is bigger than 0. Is it always bigger than 0?
It is if x is greater than 1.
It is if x is greater than 1, or, even x is bigger than 0, right? But x is bigger than 1 is not an incorrect statement, and so you can say that as well. And it was only required that f of x be positive from 1 to infinity, right? Or eventually even, really. And then decreasing. Okay, so for this one, I don't think it's obviously decreasing when you have an increasing function over an increasing function. It's totally not obvious. You can use an algebraic argument to show that. I think Caleb showed you guys that in recitations. Often I've had students do it that way and suck real bad at it. Okay, like as in they can't actually prove it, and once you get more complicated stuff, it's not easier. I think it's just easier to use a derivative. Yeah.
Since the top one is going to increase slower than the bottom one, can we just say that it's also kind of biased?
No. Unless you prove some general statement, no. Like, no.
Like the entire function by.
Guys, the way you prove a function is decreasing is you use the derivative, okay? Like, that's what the derivative does. And we're going to make you, like, check that. I'm sorry, it's just, it is what it is. Unless you want to try to prove some general statement about the relationship between them and, like, there's some kind of big O thing, I don't know what it is. Like, there might be something I don't know about, but I think it's probably trickier to prove than just doing the derivative a few times.
Why are we doing it for this one and not the last one?
Because the last one had a constant in the numerator.
Oh.
So you have a constant over an increasing function, as in like a constant over something with x's in it, as long as that thing in the bottom was increasing, that means that it decreases. That's pretty easy.
Okay.
But this one, when you put stuff in both places, it's just easier to use a derivative. Okay, so a derivative would be low d high, so 2x times 1 minus high d low, which is 2x. Did I boo-boo?
No, that makes sense.
Nope, Aww. This is why, nope.
Tiny one.
F of x equals, oh, because I'm also still in the eraser. F of x is,
Greater than 0 is what you had there.
if, okay, and then, okay, let's redo that derivative. So I'll just make you think, since apparently I don't have a brain this morning. Okay, so low d high
Yeah.
minus high d low. Did anybody else teach you that rhyme? Okay.
I learned it from you.
Okay, well, yeah, that's because I had you for Calculus 1, so I know you learned it. So I think when you simplify, you have x squared plus 4 minus 2x squared, right? Which becomes,
Negative 1 over x squared plus 4.
I think it's 4 minus x squared over x squared plus 4 squared. Do you guys buy that?
Well, if you take out a negative and make it x squared plus 4, then you can cancel out.
If you take out a negative, it doesn't become x squared plus 4. If you take out a negative, the 4 negates, right? So no, nothing is going to cancel. Does that make sense?
Actually, you could factor the bottom.
Does x squared plus 4 factor?
No, not that. It's got a squared, so you can make it negative x squared plus 4 times negative x squared plus 4.
Okay, no, okay, we're gonna stop doing that, no, the x squared plus 4 is a prime polynomial, does not factor, but anyhow, but the point is, if you're looking for where a function is decreasing, you're looking for the derivative, where the derivative is doing what? Positive or negative?
Negative.
Negative, so this thing is less than 0.
Yeah,
If-
we need to go farther.
You don't need to go further. What's true about x? And this is just simple reasoning. The denominator is always positive, no matter what the heck you put in, right?
Yeah.
What number, once you go past it, is going to make your numerator negative? 2. Once you plug in things that are bigger than 2, like 4 minus 2 squared makes 0, right? But 4 minus 3 squared is all of a sudden negative, right? Because 4 minus 9. So this is less than 0 if x is bigger than 2. I don't know why I just wrote 0. I hate it when my brain and my hand don't agree. Not equal to. Like equal to 2 would mean this derivative is 0, but as long as x is bigger than 2, this function is decreasing. And the requirement of the integral test was not really that the function had to decrease like from 1 on, it's just as long as it eventually decreases. And so this one decreases from 2 on, and you can just think if I had to do my little proofy thing again, I could just like leave the first term off and then add it back in. Kind of like we did with that first 1 over x squared one. Yeah.
Okay, so like 3 squared is equal to negative 3 squared, right? So why wouldn't
If your question is about why something doesn't factor, ask me after class, okay?
It's not about why something doesn't factor, it's about why we couldn't have taken the entire thing inside the square, the second one, not the first one, and made it all negative, and then tried to factor.
Later. Okay, I don't even know what you're trying to get at, so not now. Okay, so let's actually do the integral test. So at this stage, we integrate this function from 1 to infinity, x over x squared plus 4. Is this another example of arctan? Why or why not?
No substitution.
I don't think so.
No, because there's an x there. I think somebody said that, right? Okay. All right. So would you feel more comfortable if I did a substitution? Because I don't mind. Okay, so what would you let u equal?
X squared plus 4.
Okay. And then du is 2x dx, so we'll put in half du was x dx, okay. If x is 1, what's u? 5. And if x is b, what's u? B squared plus 4. Okay, you have to do that as well. So you have the limit, b goes to infinity, integral from, 5 to b squared plus 4. And I think that's just 1/2 times 1 over u du. Is that all right? I know does anybody feel like it's a little bit weird to have an upper bound be like a function? That feels like a little bit strange.
No, it works.
Not to anybody? It feels strange to me, but it works.
It's because infinity.
Infinity squared plus 4 is still infinity, right? Okay, so limit b goes to infinity. The antiderivative is 1/2 natural log absolute value of u. But those absolute value bars aren't super necessary here because of the fact that you've got positive things. So that's equal to limit b goes to infinity, 1/2 ln b squared plus 4 minus 1/2 ln of 5. Okay, so is this going to go to a number or is this going to go to infinity? It's going to go to infinity. Wow.
But the natural, well, no, it doesn't matter what happens.
Doesn't matter what this is, right? Because this goes to infinity, taking off a finite thing doesn't change infinity. I tell my sister I hate her infinity plus 1, I still hate her for the same amount as infinity, right? And that's what we used to say when we were kids. There's something wrong with us, all of us. Okay, so, write your conclusion. So since the integral diverges,
And write the
squared.
integral, not
I think
say
probably,
the integral.
yeah. If you say the integral, probably it's also correct. But I think it's probably good to be specific so you guys know what you're talking about. Because I think Caleb had a little bit of a good time telling you guys that you were not allowed to say it. You can't say it converges because we must know what it is, right?
Can we say the integral?
Even though there's
Sure.
only one function in
And
the
then the
entire thing we were
series.
working with.
Sure.
We don't have to write either of them.
I think, let me plead the fifth for just like until tomorrow, okay? Let me ask but I do think that would be okay, but I have to double check what Professor Faudree wants, okay? Let me just check, yeah.
So even if it was only decreasing after like x equals 900.
It'd still be fine.
And you don't change it's still always 1 to infinity.
It's fine.
You go to 900 to
Yep.
whatever. Okay.
And it's because that approximation argument we made, that when we do proxies, you can just draw it from 900 on, and then just add in the first 900 terms that have to be finite in any way.
So you
That's the
still apply the
reason.
integral test with 1 to infinity.
Yep.
Just plug in whatever.
But you just tell me the point from which you start decreasing. And that's kind of what we're looking for. If you have to use a derivative, we're making sure you know, like, I know this is negative from this point on. Then you and then you, okay.
Doesn't the series diverge?
Oh my gosh, yes it does, of course. Is it the same question? Yeah. Yeah, the integral diverges, so the series also.
Question that.
Yeah, how did you not question that? Sorry, my bad. Oh my gosh.
I was so lost.
No, they do the same thing. That's the point. Okay. Gosh.
I was just like, sure, that makes sense.
All right. So confirm that the integral test can be applied to this and then use it to determine the convergence or divergence. Okay, so
Definitely have to
first,
do derivative.
yeah, definitely have to use a derivative to prove the decreasing here. So it's a continuous f of x equals e to the 1 over x squared is certainly continuous on, given an interval,
Anything bigger than 0.
1 to infinity or even like 0 to infinity, right? 0 is a problem. As long as you make a true statement, we won't dock you points. Does that make sense? If you said all real numbers, then that would be false. Does that make sense? Okay. It's positive. Is it positive? I think it's actually probably positive everywhere, right?
Well, no, if you put in a negative n, then No, wait.
For all x not equal to 0, because technically you can't plug in 0, right? But putting in even a negative x, the e to the anything is positive, right?
Yes.
And then the denominator is positive. So, okay.
That's why I cut myself off.
Oh goodness, decreasing. F prime of x. Have you guys learned that you actually don't ever have to use the quotient rule? Did somebody just say what?
Why'd you bother to teach it to us?
Well, I think, I don't know, this way is, they're both good. I can rewrite my function like this, and then what kind of rule can I use? Product rule. You can prove the quotient rule using the product rule. Like f over g you can write as f times g to the negative first, and then you can use the product rule and the chain rule to prove the quotient rule. So, okay. So using the product rule on this f of x equals e to the 1 over x, which is actually the same thing as e to the x to the negative 1, x to the negative 2, right? It will simplify actually quite nicely. So we'll do the hard part first. What's the derivative of e to the power x to the negative 1 power? E to the x to the minus 1 times the derivative of x to the minus 1, which is negative 1 x to the minus 2. Do you buy that? That's because the derivative of x to the negative 1 is negative 1 x to the negative 2. Right? That's the power rule. Okay.
Why did x to the negative 2 just pop out there?
Well, because you have the derivative, the product rule works derivative of a first function
Oh.
times, this is the second function, right?
Yep.
Then e to the x to the negative first times the derivative of x to the negative 2, which is negative 2x to the negative third. Some of the think maybe people said that. It's kind of gross, but there's a big old greatest common factor, isn't there? They have e to the, I'm going to write that as 1 over x again. They have e to the 1 over x in common, right? Can't you also take out a negative? Do you buy that? And could you also take out x to the negative 3?
How is that? Oh, I see.
Because right here, what happens when you multiply those two things together? What happens to the exponents? They add, and that becomes x to the negative 4, right?
Yep.
So when you pull out x to the negative 3, I think you're just left with now x to the negative 1. And then plus 2. Okay, so that's negative e to the 1 over x cubed. And this is 1 over x plus 2. Professor Fabry didn't do it this way in her notes, but this is not bad. At this stage, what would you have to do? I would say get a common denominator there.
Wait, haven't you already proven that it's negative by having a negative in front of the e?
With certain conditions on x. Let me just show you by doing one more step, okay?
Okay.
So negative e to the 1 over x cubed times, if I say 1 plus 2x over x, do you guys believe me? I just got a common denominator multiplied by x over x, right? Okay, so that's the same thing as negative e to the 1 over x times 1 plus 2x over x cubed.
Why didn't I
Should be, nope, I boo-booed, that should be x to the 4th, okay. Okay, great. So there we go. This is less than 0 if... Okay, so the x to the 4th is always positive, so don't worry about him, right? This e to this stuff is always positive, so this term is definitely always negative, right? But you gotta be careful that this 1 plus 2x, if that were negative, then you have a negative times a negative giving you a positive, right? So this top term will remain negative as long as 1 plus 2x remains positive. Does that make sense? So 1 plus 2x bigger than 0, and if you solve that for x, you get x is bigger than negative a half. which certainly is true for x bigger than 1, right? That's what we needed. Oh goodness, sorry. Now we get to do an integral.
It's the last little sliver.
It's the last little sliver of paper. It's actually not a very hard integral, it's a substitution. And that's one of the reasons I put it on here, because the integral is a bit tricky if you don't look at it the right way. Like if you try to do integration by parts, you're just gonna, that's not the right method. So, given that I told you that this is substitution, what do you think you're going to let your u equal? 1 over x. And then du is, we already did this, right? Negative 1 over x squared, isn't it? And that's almost what you have in your integral, right? So all you got to do is fuss with the negative a bit and move the negative over. So negative du is 1 over x squared dx. Okay, if x is 1, what does u become? And if x is b, u is 1 over b, right? So that's the integral negative, integral 1 to 1 over b, and I think it's just e to the u du, right? If you dislike the fact that you have a negative sign there, what could you have done to make it go away? Flip the integral, which we put the 1 over b on the bottom and the 1 on the top, that would also have been fine, okay? Like you could do that in one step, I don't care. We don't have to do that though, do we?
Yeah.
No, okay, so let's just not to save space.
Wait, isn't 1 over b just 0?
One we get, don't try to skip steps, but it will, yes. So negative e to the u, evaluated from 1 to 1 over b. I think you're just a little bit ahead is all. Negative e to the 1 over b plus e. So now you can tell me what happens. What happens to the 1 over b as b goes to infinity? Goes to 0, and then so that goes to negative e to the 0 plus e, which is, as people were saying, negative 1, e minus 1.
Could we have just skipped that second to last step there?
Yes. Since the integral, I'm going to be lazy myself, converges, the series does what? Also converges.
So technically, you have to say by the integral.
Well, in this case, since I told you what to apply, no, but when we get to the questions where we're going to have tests all mixed up and you've got to choose them, we'll just make you state at the beginning like what test you're using. Yep, otherwise you'd say by the integral test.
Probably easier to state at the beginning.
Yeah. Okay, how about this guy? So this is one of those instances where you don't have to use a derivative. And it's also an instance where using a derivative is going to be really disgusting. Can you see why?
Yeah.
Because you're going to have to differentiate n times ln of n squared, which involves the product rule and the chain rule. Does that make sense? So for stuff like this, when you only, the difference for, or the thing I want you to distinguish is if your function in the denominator is an increasing thing, 1 over it is decreasing. And then you can just say, okay, this thing is increasing because of that, and no need to use a derivative. And for stuff like this, it's particularly useful.
Does natural log of 0 exist?
No, but, no, it does not. Okay.
So 0 still will.
But whoa, look at where does the series start? 2. Why is that?
Because 1 doesn't
Natural log of 1 is 0, and then you'd have 1 over 0, right? That's why this one begins at 2, but that's not important. Okay, well, I mean, that is important, but it's not important for applying the integral test that this begins at 2. Okay, so continuous first.
X is greater than...
Yeah, exactly. If we have f of x equals 1 over x ln of x squared is continuous so long as x is bigger than 1. How about positive. And this might be a little bit, well, it's not tricky because ln of x is squared.
Wouldn't it just be positive for everything?
For everything where you have stuff is defined, right?
Yeah.
So let's just say x is bigger than 1 because, you know, that's certainly true. You could be more specific, but you've got to be careful about, like Professor Faudrey on her notes, she said positive for x bigger than 1, so let's just go with that. So I think it's technically positive between 0 and 1, but not including those as well, but it's not important. Okay, so decreasing.
For all real numbers?
Yeah, well, since
For all existing numbers.
x ln x squared is increasing, f of x, and this is only true for x bigger than 1. Maybe it's true for more, but true for those for sure. F of x is decreasing.
That integral doesn't look any nicer though.
Well, a lot of these integrals that, and we're anywhere from 2 to infinity, since the series began at 2, that's how you deal with that. A lot of these integrals can be computed using substitution. That's why I picked some, what I think are a little bit more tricky ones to remind you that substitution is a method you should know. It's just been a while since we used it because we did other harder methods. So what would you substitute for in this guy? U equals ln x. I should probably do the limiting thing first though. So limit p goes to infinity, integral 2 to b 1 over x ln x squared.
I just realized that d is a function technically, so either way.
Du is 1 over x dx. X is 2 means u is ln 2, and x is b means u is ln b.
I think I see what this is.
I think it's just u to the minus 2. Do you guys agree?
No, wait, what about that x in front?
What about it? Why is it gone?
I know x gone.
It's part of the du. Does that make sense? Okay. So what's the antiderivative of u to the minus 2?
Negative u to the negative 1.
Great. Negative u to the negative 1. So we have negative 1 over natural log b plus 1 over natural log 2. Yes? So natural log of b, as b goes to infinity, that goes to infinity, right? 1 over infinity goes to 0, so this just goes to
1 over natural log of b.
good job. And as the integral converges, so does the series.
Wait, is 1 over natural log of 2 to the negative 1/2?
You could write that as natural log to the quantity, as long as you put your powers like in a nice, as long as you do this. So it's obvious that the whole thing is to the negative 1, not just the 2. Because if it's just the 2, it's actually different.
So that wouldn't be negative 1 times natural log of...
Nope, because there's a, I can, after class ask me, I can prove to you why that rule doesn't work, okay? Like, because there's a reason.
Parentheses.
Yeah.
Not that.
Okay. So one thing we did, is everyone okay with this example? That's kind of the end of the examples that are tricky integrals. We're going to move on to other things for a little bit, okay? So one thing we did in the section 7-8 about improper integrals is we talked about, I think that was that section. We talked about the integral from 1 to infinity, 1 over x to the p. Does that ring a bell? This is definitely on your 7-8 notes. Like we did this integral, and if p was a specific value, you could say this integral is going to converge. And if p was some other values, you knew it was going to diverge. Do you remember what those values were?
Less than 20.
Converges if p is
Greater than converges if p is
Greater than, it such as this is really greater than 1. Like things like 1 over x to the second, 1 over x to the third, those things converge.
You mean the absolute value, right?
Nope.
Does that account for, like, if it was 1 over 3 halves x to, I mean, 3 halves to the power, x to the power of 3 halves?
Yes. 3 halves is bigger than 1.
Right, but is it only, I guess, it's not only.
It includes rational powers as well. Yep. You could have 1 over x to the pi, for example. I mean, really, and that would also converge. Like you could, like compute the integral, like do the antiderivative, and you're going to get that it converges every single time. And it diverges if p is less than or equal to 1. I think that was an example that was the extra credit question on the test, right? Something whose area was infinite, but its surface volume was, when rotated, the volume was finite. And if you integrate this, 1 to infinity, 1 over x, that integrates to ln of x, and ln of infinity is infinity, right? And that's also true if you had like 1 over x to the 1/2. What if that p were a negative number? Because it worked for those as well. What if you had 1 over x to the negative 2? What is that actually?
X to the
It's actually just the positive 2, and you would agree that the area from 1 to infinity under x squared is definitely infinity, right?
So
Okay.
why was it written that way when that's obviously leaves you a hole where neither converges or diverges?
There's no hole.
No, not what you wrote, what they wrote.
Well, I think the reason that they do that is because you almost never, I don't know, I think it's because you almost never see things that are written as 1 over n to the negative 2 because that's just silly, right? You just reciprocate it. Does that make sense? So I think that's the reason. And so using that, you have this thing which is called a p-series. It converges if p is bigger than 1, so same as the rule for integrals, and it diverges if p is in between 0 and including 1. And for things like that, you don't have to do any work at all. You can just say this is a p-series, p is equal to this, therefore blah. Like no work at all. And so we're going to need that because we're going to want some series that are quick and easy to compare to, and these is a family of things we kind of know what they do.
So that's kind of related to the geometric series, the A over R.
Yeah, so the other series we know quickly is a geometric series. Yep. Okay, so this one, but you're right, there's a quick way to look and see if it is convergent or divergent.
You also
So
write
this
that
is
1 over n to the 1.
a p-series. What is the power equal to? 1. And so this diverges. And it's much, much, much easier to prove that using like an integral test than the way we did it back in section 11.2 with partial sums. That was super tricky and cumbersome. I should just take it out and put it with the integral test, but the problem is they put it in section 11.2. Dang book. Okay, this one, what power is n times root n really? 3 halves. Does the 2 in the numerator really matter at all? No, not at all. So it's a p-series. P is equal to 3 halves. This converges. Why do you think they use the letter P?
power.
Power. Yeah, some logic there. So this is the sum. Oh, when you have a fifth root of something squared,
It's 2/5.
it's 2/5.
That doesn't sound greater than 1.
That does not sound greater than 1, does it? It's a p-series. P is equal to 2/5. This diverges. So is that all right? Okay, that should be really easy, right? Those are like, just figure out what the p is, how does it relate to 1, make an easy conclusion. Okay. If you forget that, you could do the integral test. Like, it would be really easy. All right, so if you know something converges, a reasonable thing to ask yourself is, what does this stuff add up to? Does that make sense? As a question? And obviously, you're not going to add an infinite number of things because you don't have infinite time, right? So you want to ask yourself, like, how good is my estimate if I add up 100 things or 1,000 things? And at what point in time is it just, like, good enough? Okay? So assume you have a convergent series. So assume we have a convergent series, sum we'll just say n equals 1 to infinity of a sub n. We're going to estimate, and I'm gonna like give this a name. Let's like call this equal to something s. We don't know what s is, but it equals some number. Like, because we know what converges, so s equals some finite number.
Should we also say s doesn't equal infinity?
Well, because it's convergent, it can't, right?
Okay.
That's implied. So we estimate s with a partial sum. And that partial sum just means you add up part of what's there. And let's call that s sub n, and that's a1 plus a2 plus a3 up to blah, 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 up to an. Does that make sense what Sn is? Okay. So, I want an expression for the leftovers, which is called the remainder. So, Rn is going to be my remainder. And the remainder, not like a remainder in division, but like the remainder of stuff you have to add up. Does that idea make sense? So if you stopped adding at a sub n, what do you have left?
Everything between a sub n and infinity?
Yeah, a sub n plus 1 is the next one, right? A sub n plus 2, is this one going to actually, no, s sub n ends. Is r sub n going to end? No, so etc. So that's all the leftovers. Does it make sense that this r sub n measures how much you're off by? Like, this is your error. This is how much you're missing. Yeah, so this r sub n is the remainder slash it's the error. How close you are. How much you're off by. And we're going to be able to estimate that.
If we square that.
Now, I'm going to draw two pictures. I want you to draw them. We'll talk about how they're useful, okay? They're going to look a little bit like what we had before. So we have n plus 1, n plus 2, n plus 3, and we have some positive decreasing function because we're using assuming we can do the integral test. So draw this picture. So this picture is pretty similar to what we drew when we first started to kind of use integrals. Yeah?
Why isn't there an n on the second?
Well, I just don't need that point, but there could be an n right there. It's just like, I just chose to start them in different places, that's all. There's no reason. Okay, now let's talk about what the area of the boxes are. Do you buy that this box in picture 1 has area a sub n plus 1? Because its base is a width of 1, right? Its height is what you get when you plug your number n plus 1 into your function. And your function, like, gives you out that term in your series. So that's the whole f of n equals a sub n. Just that instead of a sub n, it's n plus 1. What's this next box's area going to be? A sub n plus 2. This is a sub n plus 3. And that's because the thing that you're plugging into the function, in this case, n plus 1 is what gets plugged in. N plus 2 gets plugged in. N plus 3 gets plugged in. This one, what's the area of my first box? What gets plugged in? The height is found by using n plus 1, isn't it? Okay, so that is a sub n plus 1, a sub n plus 2, a sub n plus 3. Those are the remainders, aren't they? Like if you went on to infinity, that is the remainder. Okay, so r sub n we're going to stick in the middle. I want some integral that's bigger than it, and I want some integral that's less than it. I actually drew them on clever sides. Maybe. I don't know if I did. Okay.
Now get why you drew them in parallel, not on top of each other.
Okay. So do you agree that the remainder has to be less than the area under this curve? Does that make sense? So that would be an integral from where to where? N to infinity of whatever your function is.
Wait, the remainder has to be less than the integral of the curve on the right?
Nope, looking at the curve on the left.
Okay.
I did draw them, I should have drawn the other way. So that one comes from that picture. But do you buy that from the picture?
No.
No, you don't buy that? Well, isn't the remainder comes from adding up an plus 1, an plus 2, an plus 3, doesn't it?
Okay, yeah.
So the remainder is the sum of the areas of all those boxes.
Okay.
The area under the curve includes those boxes plus those bits.
Okay.
You buy that? So that's why the remainder is smaller than that area under the curve.
Oh, okay.
Does that make sense?
Yeah.
Okay, cool. This other curve is shifted over a bit, but the remainder is the area of these boxes, right? And the remainder is bigger than the area under the curve, but in this case, the starting point is n plus 1. That would give you a lower and an upper bound for the remainder. Honestly, more often than not, what we use is this case. Like we just use that half of it. But it has to do with the fact that you can think of the remainder as adding up the areas of these boxes, and then when you do an integral, you either get a little bit of an overestimate because you get the total area, or a little bit of an underestimate because you get total underestimate because you leave some stuff off. And those boxes work the way they do because the function's decreasing. If it wasn't decreasing, this wouldn't be true. So, but what you can do to estimate your remainder is just integrate from n to infinity. So let's do that with something where we like left a thing off. And how accurate your estimate is will depend on how quickly your terms go to 0. Where a term going to 0 doesn't mean it converges, but it has to happen for it to converge in the first place. And the faster things go to 0, the less things you're going to need for approximation. Like 1 over x to the 5th takes fewer terms to approximate it to a certain accuracy than 1 over x squared, for example. Okay, so there's the remainder estimates on your paper. That's example 8. So approximate this by using the sum of the first 10 terms. So that would be partial sum s sub 10, and this is a calculator question, but tell me what you're going to punch in the calculator. First you plug in 1, so that's 1. Then you plug in 2, which gives us, then you plug in 3, which gives you, and one more. Plug in 4, you get, what's the last thing you plug in? 10, which would be 1 over 100. Like, just tell me you know what the pattern is. If there's 10 things, you can do ... You get, and then don't get a common denominator, for the love of God, use a calculator, okay? Like, this is approximately equal to 1.5498. And I think WebAssign probably tells you to give it a specific amount of digits. I hope I specified on the quiz. It probably got smart and did. Okay, so the error is equal to the remainder with 10 terms, which you just proved is less than or equal to the integral from 10 to infinity 1 over x squared dx. And to apply this test, you have to know the integral test applies. This is a p-series, and the integral test applies to p-series. Can you now do that integral? Not ridiculously hard, is it? So it's the limit as sum b goes to infinity, integral from 10 to b, x to the negative 2 dx. So what's that? Negative 1 over x from 10 to b. Negative 1 over b plus 1/10, right? So what does that equal? 1/10.
We're off by 0.1.
You're off by at most 0.1. Like that's an overestimate of the area, of the error, not area. So the value.
That's pretty good.
That's pretty good, I think. Just 10 terms. The value of your series, sum equals n equals 1 to infinity, of 1 over n squared, is at most 0.1 more than your S10, your estimate. How would we know that this is an underestimate? It's a really easy explanation. What happens when you add on more things? What are the things you're always adding? They're always positive. Does that make sense? So because you've always left off positive stuff, you're always going to have underestimates. Okay. Kind of a cool question that you can answer is that, so we know that, okay, well, we picked s equals 10 and we had a certain accuracy. Now we could say, well, how many terms do I need to have that much accuracy? So what you want to do is you want to find an n so that r sub n is less than 0.0001. Does that idea make sense? Okay, or how you can do that, you know that r sub n is less than the integral from n to infinity of 1 over x squared dx in this case, right? So couldn't you take that and set that less than 0.0001 and then try to solve it? So you can take this thing and you're able to solve it for n.
Would that involve a derivative?
It's not, it's going to involve an integral. Okay, so watch how this works. Didn't we already anti-differentiated this guy, didn't we?
Yeah.
So only difference here is we'll have the limit b goes to infinity, integral n to b, x to the negative 1 dx. We want that to be less than 0.0001. I don't know why I wrote negative 1/2. That's obviously incorrect. It's negative 2. So what's that? Negative 1 over x, n to b, less than 0.0001. Okay. So what happens to that expression as b goes to infinity? What does it go to?
1 over n.
Becomes 1 over n. Okay, and I think, did you guys buy that? I think it's actually easier in some cases to write decimals as fractions using like just placeholders and the fact that it's base 10. So you got tens, you have the tens, hundreds, thousands, 10,000s. Does that make sense? So that becomes 1 over 10,000. And as long as you multiply inequalities by positive numbers, there's no flipping of the inequality symbol, right? So couldn't I kind of just like multiply n over and to the right side and 10,000 to the left side? So end up with 10,000 is less than n. Or if I just flip that, so n is bigger than 10,000.
Can't you say greater or equal to?
Yeah, you probably can say greater or equal to because there was to within 0.001 might include an equal to. We'll try not to be picky about that because it's fairly specific, right? Yep.
A basic notation question, so you don't need equal signs for each line?
No, it's kind of like, it's a good question. So like when you're solving an equation like 2x plus 3 equals 7, you don't put equal signs between those steps, do you? You just say, oh, 2x equals 4 is my next step, right? And then x is equal to 2.
Oh, right, because you have your less than or equal to.
So the less than or equal to kind of functions like the equal sign there. And what you could just say, like I said, something like, you could say like implies, like that implies this, which implies that, right? That's okay, but you don't really need a symbol for this. So it's just kind of general practice, and your book does this too, so you can look there for examples of like good notation. They just kind of like line up the or equal to signs and just kind of do this equation leads to that equation, which leads to that equation. Because if you put equal signs throughout this stuff, you end up like saying weird stuff like 2x plus 3 is equal to 2, or because equal signs carry along. Okay, so does that make sense how you pick it, how you find the n though? So you end up with integrating the function just from n to infinity and then doing the limit, and you have to solve that for n. I think we're going to skip example 9 because it's not very hard, and I want to say one thing about example 10, that to know what they define 5 decimal places to be. So here, when something is asking for certain decimal places matching, their definition of that is that r sub n is less than or equal to 0 followed by 1, 2, 3, 4, 5 zeros, and then a 5.
How would that be a 5?
Some technical stuff having to do with rounding. I'm afraid I'm not prepared to really explain it super well, but that's what you do. And I think there's probably a definition of what it means to match to 5 decimal places, and it probably has to do with a difference. You take the actual thing minus your estimate that it's less than this. And the first 5 zeros mean that those first 5 places should match, right? I think the fact that this is 0.5 and not something else probably has to do with a definition of what this means to match enough.
It doesn't always round up.
No. So, but the point is that if I said 4 decimal places, you'd have 4 zeros and then a 5. I prefer the things where they say like within 0.01 and they give you a specific number, but this will also occur, so just be aware that's what it means and solve your problems accordingly. Okay, so that's it.